Hi, everyone. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Vadum with Atlanta Functional Programming. The last couple of weeks, we've been talking about method combinations and the exploration of method combinations, but we took a digression to explore the lparallel library in an effort to start a small little project, but I think an important one to kind of show you the use of method combinations by creating kind of a lparallel task workflow like method combination where you can decorate your class methods with this method combination in order to do kind of like a MapReduce style task-based workflow inside Common Lisp without too much code. As I started digging into the actual method combination last week after our episode, I decided that it might be more important to finish off the completion of the lparallel library itself because there are a couple of other concepts in the lparallel library that might be useful for our project, mainly the concept of promises and cognates and things like this. Some of which I myself have not actually encountered or used. Thought it would be pretty useful for our exploration as I was reading the documentation. And I thought if it'd be better to complete that, and then as soon as we come back from our temporary hiatus in July, at the end of July, we can start on this little project. Before I begin discussing the remainder of the L Parallel Library, a couple of announcements. For the next couple of weeks, that is the week of July. I think it is next week due to the 4th of July weekend, as well as the following 2 weeks. Forgetting the exact dates right now off the top of my head, until July 27th, where the uh, Common Lisp Study Group is going to be on a hiatus. So get your weekends back for a couple of weeks. I hope to see you guys back at the end of July. Um, as usual, this is an ongoing announcement. Atlanta Functional Programming is looking for talks both online and in person. If you have a talk topic that you are interested in presenting, feel free to reach out to me and or Judd Taylor, my co-organizer. Um, I'm I'm present as Bugram on both functional programming Slack as well as for the Atlanta locals on Tech 404. Um, and for those of you who are on the Lisp Discord server, you could also reach out to me there for giving talks on either in the Common Lisp Study Group or a separate talk related to functional programming and or Lisp. Um, and we'll get you scheduled. Um, Also, we will be planning on beginning our another book club, so to speak, in the Common Lisp Study Group in starting in August, and that is on paradigms in artificial intelligence programming by Peter Norvig. I think it's an appropriate book to start now, given us being in kind of like an AI summer with not just ChatGPT and LLMs being at the forefront with NLPs as well, but PyTorch and the GPUs and TPUs used in machine learning and machine learning techniques advancing on top of uh, the obvious existing successes that we've had in the past decade. It'd be always important to kind of revisit such a book, which actually does what other artificial intelligence books tend to ignore, which is they're more focused on the actual algorithms themselves and teaching up the particular concepts, whereas um, Norvig, with this particular book, compared to his traditional AI book, AI Modern Approach, decided to start with kind of what he calls a first version of different concepts. Um, in artificial intelligence and then work his way into something close to production level programming inside Common Lisp, which I thought was pretty neat. Um, we'll go chapter by chapter. It will give you a good overview of classical techniques, both in Common Lisp and in artificial intelligence, and we'll work our way up. And in some cases, it is my goal, at least through our ongoing discussions, to see if we could expand some of that into some stuff that's happening today with obviously state-of-the-art research and or um, it's kind of production ideas that we can actually write to make advanced versions of what is already presented in the book. But I'm not going to jump too much ahead. Just an announcement for folks who are looking ahead to go ahead and kind of grab the book if you can. It is available, I believe, online. Um, I think the publishers gave Norvig rights to be able to publish the PDF of the book somewhere. But in addition, you can always grab a copy from Amazon, which I would encourage you to do because a paper book is always sometimes pretty nice to have. Last week we kind of ended our discussion in lparallel with actually something of this kind, which is the defining of functions that allow you to create parallel versions of tasks. Okay. Um, there are a couple of other things that we can actually tend to do too as well, which is a the ability to actually take your task pool and make every worker inside that task to do a particular function. All right. So if you wanted to like separate and do what um, what you would normally do in CUDA, which is do data work splits and then being able to do data parallel programming where a subset of the data can be actually used to do some sort of transformation across each thread in a single program multi-data type fashion. You could do something similar in lparallel with something called broadcast task, and we're going to actually go through some of that today because I noticed that in the last version of lparallel they actually introduced this concept. Um, but to start with, I thought we would um, look at error handling first with uh, lparallel. lparallel, as I mentioned, creates task pools, which we saw with the notion of kernels here. If we go and look at here in uh, start kernel using where is it? It's yeah, lparallel make kernel, and then we actually end up specifying the number of threads or workers we want as part of our task pool, and then we can actually go and run um, our tasks on these in this task pool. But what happens if an error actually ends up being thrown inside of a task is important to kind of think about. In the case of uh, lparallel, each of these are actually uh, going to throw an exception or a condition up to the top of the thread, and then usually just if there isn't a condition handler, it'll end up um, just ignoring that condition with some default restart that's provided by lparallel, and you can actually go ahead and use that default. But lparallel, in addition, gives you the ability to provide your own handler binds for particular conditions that you may encounter. And I thought going through this example that I saw in the documentation would be pretty useful. So the first thing we would have to do is first define a condition. Okay, so let's first here create our worker because hold on, I'm going to restart the REPL here because I did some work here earlier and I don't want any issues. And let me go and load AFP method combinations, which includes our lparallel library. Okay, let me do this instead. Since we're not going to be dealing with method combinations today, let me go ahead and, for the time being, just go ahead and load lparallel directly. And then we'll just use a new namespace and create a scratch buffer here. Just to get things started. Okay, and here, let's move this down here. Okay, and let's go ahead and create a quick package. So this way, because I like to keep my stuff isolated from the global CL user package, just so if there's an accidental name collision, I don't have to worry about it. We'll do AFP lparallel tutorial. Obviously, we want to use CL lparallel just so that I don't have to namespace everything. Generally, I don't like the idea for doing this use package because that also causes name collisions potentially. But in this case, since we kind of gotten used to actually knowing what is inside of the API, it'll be pretty useful for us to actually, you know what? Instead, I'm just gonna do what I normally do. I'm just gonna go back on that. I normally don't like doing this just because, again, it ends up having some issues when you start defining symbols that you don't realize are part of the parent level package, either whatever you provide. Normally you don't want to actually override any symbol that's already defined in CL, which is why UCL is pretty safe. But other libraries, there might be a situation that ends up having some issues. So let's go ahead and load lparallel here. There we go. This is compile loaded. Okay. And let's go ahead and create our standard kernel because we want to make a kernel, not allow other keys. I did not mean to do that. I need to fix this. Okay. How many is this? Work account, we'll just go ahead and make 10. We don't need to do binded context right now because unless you're doing thread local variables, it's not necessary to worry about that for now. But keep that in mind. Bindings and context is available to you as a review for folks who have not been here or remember from last week. Okay, so let's go ahead and create our first error. Okay, we're going to define it as a simple condition. Okay, remember conditions is defined with define condition. Conditions are classes; they are objects for Lispers who don't remember. But it doesn't use def class; it uses define condition instead to specify the errors. I'm forgetting the exact reasons why. It's part of the standard though. Uh, so we can always go look up that at some point. And we need to always specify that we are actually going to be subclass from error, which is the standard error class. So most classes are actually subclass from standard object. If you recall, internally it's already implicitly done that. All conditions are subclass from error. Okay, so we now have our error. If we go and look at this, it is a macro that ends up calling the kernel define condition internally. You don't need to worry about too much about that, but I thought it's important to just quickly review that. Once you have your error defined, you can now provide a task handler bind using lparallel task handler bind. And this is going to be a function. It's like an flat, right? So you're going to specify the error, okay, first that is going to be binding to, and then this is going to be the lambda that takes in the error. We can actually specify um, the use of this variable. In this case, this is the actual exception being passed in. There's going to be only one exception here that's being passed in. We can also look at the internals of that later on if we need to. But for now, we're just going to just follow what the doc says, and this is something that you can choose to ignore because we aren't going to be using any information, but we could totally extend this to actually look at what it provides, if you will. And what we'll do here is we're going to actually invoke a restart, okay? So remember in Common Lisp, for uh, conditions and or exceptions, it's not just about throwing the condition. The restart are functions that allow you to, set up probably an adjustment of the code or data that needs to be adjusted for the code, and you can actually have it quote unquote restart the computation, continue at the level of the stack frame at which it was originally thrown at. Okay. I encourage some of my new Lispers watching today to go back and look at conditions and restarts inside Practical Common Lisp for more information, or go back to our discussions on restarts in Common Lisp in earlier videos for more information about this, because I don't want to delve into too much information on how restarts are done, because that's a talk in itself. And in fact, a more recent book by Michael Foherta on the condition system is out that actually digs into some of this information. And according to documentation, this is just nothing more than a going to call a restart that we call number 9, that we are going to define when we set up the what's it the the map car, that we're going to whenever we actually end up using this particular thing, you'll see, and what how it's going to be used. Okay, so um, once we have, one second here, I think I'm going to have to close this out. Okay, so once we have our task handler bind, this is kind of like a let form. Okay, so if you look at this, this is client handlers that's going to go into um, uh, this macro is just specifying the client handlers in the let form, and we have to specify our body of clauses here. And what we're going to do here is just going to leverage this in a simple example where we map car, okay, and we're just going to take lambda x, okay, and what we're doing is we're going to restart case, and restart takes an expression, and the expression here is for any error that we get, we're going to throw an error, foo error, and this foo error obviously is going to be mapped to this task handler bind later on. It's going to invoke the restart, okay, and when it hits this foo error, it's just going to go ahead and call this function number 9, okay, and it's just going to type in number 9. So what this is going to do is when we end up uh, running mapcar on this piece of code here, okay, what it's going to do is for each element in here, it's just going to call the restart case, and then which will subsequently jump to essentially this label and return number 9, as we will see in just a second. Um, we'd have to, when we run this, let's go ahead and may have to actually do a print here just to force it to print out. Wait, did I forget to? Oh, oh. I forgot to add this. Declare ignore x. Okay. And what is it saying? Worker threads are asleep when not in use. They're typically add the following. Oh, I forgot to start my. Okay, I forgot to. Wait, did I forget to provide my kernel? I may have forgot to provide the kernel here. Hold on one second. This is. Hold on. I'm just trying to see if because my kernel is already running. I mean, I already have a thread pool running in the background here with 10 stuff. Let me go back to my I must have done something wrong. This is submit tasks, but I didn't think I had to use submit task on this. One second. Yeah, I must have messed up. This has worked before. Let me see something. Lparallel emap vector and oh, right. I made this, but what I want to do is this. That's right. Now we will have something. Keep forgetting that I don't have to create a separate variable for that. Unwrap. There we go. Didn't actually print it out. Okay, so I have to actually do this. There we go. So you can see that when you're, and another mistake, I should have actually noticed that when I was doing this. Remember that we do, when we start our kernel threads, I actually now have two task pools, one of which is not actually being used. I could actually do this. Let me, there's kernel. Before I start, let me kill this particular kernel here. I've done this before. It was in I think it's finish kernel. I may have to do this twice to kind of get all the kernels to kind of work. Kernel. Okay. So now I can actually do this here and we can continue. All right. So now if I do parallel start kernel, we have 10. Okay. So let's review this particular piece of code again, right? So all we did is we created a condition, an error condition. We created a restart inside our map car, okay? And that restart is named number 9, okay? And what we did is we basically called the restart um, every time we encountered a variable. All right. So we collected the actual restart variable because we returned essentially number 9 every time the restart case was called. Okay. This is pretty useful for when you are doing large scale um, like error handling across multiple threads inside of a task pool. Okay, being able to actually generate, say, um, one example that you could think of this is if you are doing message like message processing for a data queue. So if you're looking at a message queue like say Kafka, or you're trying to make a Kafka like data processing system, one thing that Kafka suggests you to do is anytime you have a message that you are unable to parse, you pass it over to what's called a dead letter queue. So you can take a look at it, and instead of throwing an exception saying that this is a malformed message, and this way you could keep the process to continue to run while you are looking at those malformed messages. And one way of handling it in Common Lisp is creating this task handler bind that basically says anytime you see a malformed message error, you could just have it restart it and then throw it into a dead letter queue, and that thread is just it throws an exception and then it continues on processing the next message, right? And it's not even an exception. What it does is actually it grabs the malformed message, calls this restart. The restart will actually just go throw it into the dead letter queue, and then it'll move on in its merry way into the next process. This is a kind of useful thing to do inside of your, uh, your 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 code. Okay, for especially if you want to keep the throughput for to stay at high. Um, a lot of these kind of like designs would require extra work inside and extra handling, but you get this for free as part of using the condition system in combination with um, the uh, the lparallel library for task parallelization. Okay. What was it? You could also technically um, uh, what's it? Have this restart show up, and we could throw it up by essentially doing the following, which is if you wanted to do development on this and see the exception being thrown, you could just set task parallel to true here, and you could then run this code once again, and you could see. Hold on, I think I have to. Um, oh, right. I need to use one more thing. In this case, what you would have to do is in restart case, um, in here, we have something called um, a report. Report. and then this it'll actually allow you to um, uh, provide an error has occurred. Okay, but in order for us to do this, you got to do the following. We need to unwrap this guy so it actually it'll be you, so we don't actually run it. I mean, we run it, but we don't actually uh, throw the error message here. And interesting, it's actually not throwing. It's not invoke. It's still invoking the restart. Oh, right. What we have to do is you don't provide the case here, and if you just provide this as is, now you end up seeing as part of the foo error was signaled, you have this number 9, an error has occurred that you could end up running as a restart. And then you also get these two other errors, which is one where you could pass this up to the parent pool, okay, called transfer error. Um, and it will take the code, okay, the stack trace and whatever data that's associated with the exception, wrap it up into a closure, and then move it up the stack. All right, that's what transfer error does. Since we're actually going to deal with our default one, we're just going to go ahead and run 0, and it's going to keep passing it because we have 3 errors that are going to be thrown. It's trying to collect them, and you'll see that for each one of them, number 9, number 9, number 9 is being actually thrown up. Okay. So you have that ability to actually debug stuff. Obviously, for whatever reason, I think this is a bug here because you no. So since we provided a restart here, this is not a bug. This is just a misuse. Um, when we provided this restart here immediately in this task handler bind, we're basically telling the debugger, hey, we already know an error is going to occur in this case, but whenever this happens, just go ahead and run this default handler. Okay, that's what it's the same thing as handler bind does when you are using and when you're wrapping code that could be throwing an exception, but you don't necessarily know what type of exception that you want to, what type of restart you want to actually invoke. All right. For production level code, some folks end up actually setting it up so that you have your handler bind being in one code path, and then your debug code will end up leveraging a different other code path that just calls a function that actually does the logic. This way, you have the ability to actually use the different restarts that you provide, um, and then choose one that might be appropriate for the case at which the handler bind is required to run by default. All right. Um, all this is kind of like basic Lisp handling stuff, but it's important to kind of be aware of it. In normal day-to-day operations, when you are dealing with um, lparallel, you are going to be more or less dealing with the thread pool. All right. So in many ways, this is just a task higher level API of using Bordeaux threads. All right. They added a bunch of other conveniences for you, but effectively, you have a thread pool created by Bordeaux threads or SB threads in this case, because Bordeaux threads is a wrapper around SB threads on SBCL. Um, and you're just throwing tasks at it like you normally will if you end up having a closure on top of some sort of worker pool. So naturally, a question would arise then: what if we wanted to um, run or kill a thread? All right. Um, there is this ability, as you saw earlier when we ran this code as is without um, the protection that it had. Let me just do this. Okay, here. That you have this third option here of aborting the thread. okay, which is a member of your thread pool. In SBCL and in many other common Lisps, this is pretty dangerous in that it will kill the thread by sending it a task killed error instead. And it might actually kill it completely, in that it might actually prevent it from running and make it a dead thread. Although I don't know if you get a new thread created when you do that. I haven't tried it myself. Um, so naturally, if you want to kill a thread, this is probably not what you want to do, because you are what you really want to do is kill the task within the thread. So basically, prevent it from you know stopping the thread itself, but send a notification saying, "Hey, whatever computation I'm currently running, go ahead and kill that task." So this way, the thread is still alive and is in your thread pool, but whatever computation that is available, you can end up it will end up completing itself to whatever level of proper cleanup it can do, and so you can then start a new computation. Okay, and there are several ways of doing this. One of which is naturally, and I could show this to you by first. Let me just go ahead and do this. Um, this guy. One, two, three. Okay. By doing the following, you could do lparallel kill tasks, and you could provide a keyword argument on it, and this will actually end up um, uh, killing everything in the task pool and cleaning up everything in the task pool. Okay, this is something that the documentation calls your kill all. It's a blunt force. They call it a blunt weapon, in that basically in Linux you could do the same thing called kill all dash 9, and it will kill everything of a particular process, or kill all of a particular process category, and it will go ahead and kill even unrelated tasks. And this is essentially is like a pure cold reset. You really don't want to necessarily do this. Okay. Um, what you can do is create what they like to call is task categories. Okay. In this default that you see here is actually part of task category, which is the setup. It's an identifier that every task in the that's thrown into task pool that's associated with. When um, a particular uh, um, task is getting created, you can categorize these tasks by essentially set f this particular uh, uh, dynamic variable, and then put it in a let form, and then use it to actually um, kill off or be able to manage essentially subsets of tasks running on your task pool. Okay. To show this, we're gonna just create a dummy example in the REPL, which is basically we have essentially a channel that we're creating that. Hold on, I have to, in order for me to do this, I have to take out that closing paren, so I can actually write. And what we're going to do is we're going to go and call lparallel um, task category. We're going to actually set the task category R and task category, and we're going to set it to something called simple example. Okay. And this is a bunch of simple example tasks. And what this is going to do is we're going to end up creating a task. in underneath this task category, and we'll be able to actually then run some stuff. Okay, or that is, we could run some diagnostics. Okay, and what this does is when we submit this task, okay, there's some metadata that ends up attaching to the task. Okay, and what we're going to do here is we're just going to make it loop forever. Okay, and we're going to obviously then at this point receive the result from the channel. So we're going to go ahead and do this and say receive lparallel receive result from the channel. Obviously, nothing's going to be thrown in here, but this allows us to at least run this from some code. Okay, and what I'm going to do is I'm actually going to go ahead and cut this and put this in my REPL here this way. All right, so this way I have access to my REPL. It won't actually once it's in my scratch buffer, it allows me to then run it. And now this is running, and I can actually go in and look at my task pool. Lparallel kernel. Okay, you can see that it's 10 live. We could run this. We could see that we actually have our 10 stuff here. But the main thing is to note is right now we have a task that's being that has been thrown into this channel, into this task pool that's essentially running forever. Okay. Now, what can we do though? Because obviously this code is going to hang, right? Because this is looping forever. This is not what we want. We want to actually get something from it, right? Well, with kill task, you now have the ability to just simply say tasks and say simple my example, and it will go and kill one of the workers, all right? And then it'll throw this task killed error for you, okay? When this happens, it will also return a bit telling you that it's a success or a failure. But the point is you know that lparallel essentially had an identifier. It keeps these tasks as closures so that it can actually go in and kill them off when they need to. And there's an additional thread management that you have, which I thought was pretty cool. All right. Naturally, this is useful for debugging, but you don't want to do it during production. It's not. It's not. It's generally not a good idea to go through it during production. Um, the next thing that I wanted to talk about is promises. Promises is, as the name provided, anybody who's done stuff in features and promises as other libraries. There isn't not a whole lot to kind of go through here that some folks have not already seen in other codes, but I'm going to show you the API that it provides. All right. And to start out with this is we're going to first create a promise. Um, and let me kill that. And this here actually is lparallel colon promise. Okay. This is creating a promise. Okay. And you have a couple of uh, options in this API. Okay, the first thing is we you have the ability to test if the promise is fulfilled. Okay, with the predicate. Okay. To start off here, this is going to be set to nil when it to begin with. Okay. And actually, let me go ahead and do it this way so we know what the promise fulfilled tilde a. Okay. To fulfill a promise, naturally, there's a thing called lparallel fulfill. Okay. And fulfill basically takes in the promise object and allows you to specify a value associated with it. Okay. It could also be the result of a computation, but for the time being, we're just going to go associate with this value. Now, when we end up calling this guy, this is going to be set to true because we've called the fulfill function. All right. But that doesn't actually force the promise to complete itself. All right. You have to in order for the promise to actually complete itself, you have to do force on the promise for some reason. I don't like this kind of notation based on looking at the documentation, but this essentially is kind of like making the thread that the promise is running on essentially clean itself up. And when we run this, you can see that the it started out as nil. We fulfilled the promise, so now it became true, and then we actually now killed the thread. Now, what would have happened if we did not do this? Obviously, let's say that we took this guy out. Okay. In a normal REPL, what it'll do is you now have I think like a hung thread, because I don't think it forces the promise to kill itself. I wouldn't be able to tell you right now because since it's a list closure, I don't know. But my assumption is that since many of the code examples use this the to this force call to kind of show that the promise is closed. Now, based on what I read and what the documentation says is the importance of force isn't necessarily on calling it on fulfilled promises, but on unfulfilled promises. So if a promise is unfulfilled, um, uh, the force call essentially is a blocking call until the promise is fulfilled. So basically, here, let me just show this here. Here, if I take this guy out, it just sits there and it waits. So I'm going to have to abort and I'm going to restart my Lisp just because of the fact that I'm almost certain that me using it will end up having some problems. Okay. And let's MCL and MRS. All right. Let's go to our next thing. Just like promises is one thing, we also have futures, right? Um, a future is just like anything in other languages, but to review, it's a future is a promise that is fulfilled in parallel. A future basically runs on a separate thread, all right? And then when the thread completes its computation and returns a result, then the future is fulfilled. It is its promise is fulfilled because it retrieved the result of its computation. This is the same in other languages, but uh, the thing is in lparallel you have the same API for both futures and promises. So we can use the same API that we saw earlier, okay, where if we make this a lparallel future, okay, and this lparallel future is actually a function, okay, so it's going to do like a thread function that you can add more code to. So here you don't have to specify like a defun or anything like that. You can actually specify your body. So in this case, I'm just going to use the documentation code to kind of show what this does. And uh, let's sleep one, and let's return the address of 3 and 4. And then we could see again the same API to be used for fulfillment. Actually, let me do this. Format T future computed. In this case, we're running a computation. So the fulfillment is really whether or not the future was computed, the future value was computed. So we can call lparallel fulfill P on the future. We're going to go ahead and print this guy. We're going to wait. Essentially, let me do this. Let's do, to make this pretty fast, let's call this half a second here. And let's do sleep 1 second here. And then we could check the fulfillment. All right. Now, obviously, we want this to block. So we're going to call lparallel force on F just so that we can wait and see the thread to complete itself, right? And you can see that again, once we force it and compute it, the return value here is automatically computed to and thrown to the standard error, all right, which is pretty nice. Okay. You don't have to think about much else. The other stuff that for some details is fulfill and let me actually grab this one for example. Fulfill and fulfilled P. I think fulfill is actually a macro. So in the case of so if we grab say this code, if I can actually grab this code. Actually, what am I doing? Okay. There we go. And we print it. You can see if we run lparallel fulfill on P. Okay. And let's format all this so because I don't like stuff. Ding. All right. And we do mm. You can see fulfill is a macro to the lpromise API's underlying fulfill object stuff, so it could go make some modifications. But in this case, the 3 is nothing more than wrapped into a lambda function itself, because the fact that the lambda is what's going to ultimately be used by P to compute the value. All right. So it's essentially behind the scenes makes a fun call internally to see if it's been computed or not. All right. Did I? Okay. Okay. So this is done. There are other stuff related to futures that I really don't want to dig into. Like there's this thing called speculations inside the lparallel library, but I'm still not entirely sure how to use this. I could show some of this to you, but the use case is still like kind of gray in this. But this is a feature in this library that if those of you who are watching know how might one leverage such an object or such an API, it would be pretty useful to know. Speculations are a special class of futures, is what documentation calls it, and it it specifically is a future with a very, very low priority. So its entire reason for running is if there's no other higher priority task, the speculation will end up getting run. Uh, uh, the one thing to note is futures and speculations um, are like two ends of a spectrum. The third of the futures, well, the promises that's around is something called a delay. Um, the difference between a delay, a future, and a regular promise and speculation is one is priority and one is where is the actual computation going to be done. Okay. So in the case of futures, you're talking about um, so in the case of so you have promises that's in thread. Future is the promise is run in parallel. Promise fulfillment. This is all related to fulfilled in thread. Okay. So think of this like kind of like the promise in this case behaving like a coroutine when you run force. It'll end up reaching out to the promise and having it invoke its function. In the case of future, as we talked about, promise fulfillment is um, in parallel. So it's run. The computation is run in thread, and it's like a thread join with the result of the computation written somewhere. Then you have speculations, which are futures. So in parallel. So in parallel fulfillment. But they have low priority. So they're only run when there isn't anything with higher priority. And we've talked about being able to set a priority in lparallel tasks before, so I'm not going to review that. And then finally, I heard something in the background. Did someone's? Oh, 1 second. Finally, we have delays, and delays are basically another type of promise. But a delay is basically um, as long as uh what's the uh as long as force is never called on the delay, okay, it'll never be fulfilled. Promise which is fulfilled only when force is called on it. So these are your four types of promises that are in the API, okay? Um, they so whereas delays are fulfilled in thread, just like promises are, futures and speculations are fulfilled in parallel. Okay. And the only difference between futures and speculations is priority, and the only difference between uh, uh, promises and delays are how the force call is actually leveraged. Okay. And the one thing I will say is in the case of speculations versus delayed, now you're talking about whether you need in-thread fulfillment or parallel fulfillment. So whether or not you want a task completion to do asynchronously or versus something that needs to be done synchronously. That's the only real difference. Okay. Um, Now, one might ask in the case of delays, well, what if I call fulfill on delay? Because we just said that fulfill is uh, going to end up, uh, sorry, force is what a delay is going to end up leveraging to actually compute something, right? So let me show this example. Let's say that we create, you know, let's say we have a task that we call it deferred task. All right, it's probably a good name for it. And this guy is nothing more than a delay on some computation, let's say 5 plus 6. All right. So now when this delay is fulfilled, you'll end up getting right now. I'm just going to show you what happens when we call force, and then I'm going to reset this for the sake of this example. Um, if we end up calling deferred tasks force, you end up getting 11. But let's say that during the course of some computation, you end up saying, hey, I want you to now fulfill deferred task with the value, let's say, 5 times 6 instead of 5 plus 6, okay? And this is kind of pretty cool. You effectively changed the promise, okay? Delay hasn't been computed yet, okay? The value hasn't been computed yet because, again, remember, delay's only purpose is run the computation when asked. So when force is asked, it will actually run the computation, okay? So you can essentially constantly rewrite deferred task to different computations based on the use case. And the only time it's ever going to be computed is when force is called. So when we call force here now, instead of 11, we're going to get 30. All right. I thought that's kind of pretty cool because now you can essentially have the ability to change uh, tasks uh, in kind of like on demand whenever a particular thing is changed. But your underlying code, as long as force is called, it's going to just compute whatever the current state of the delay is. So you could totally leverage delays in one way. Speculations, though, I'm not entirely sure because I can't think of a case where you'd want to have just a low priority task that can only get run when no other regular futures are pending in some sort of queue. Like, I'd have to come with a real use case for that one. Um, so you have the what's it the force and then whether or not something has been fulfilled. So the blocking call and whether or not something has been fulfilled, right? Um, there has to be a way of knowing um, to uh, be able to hook these things together and then uh, take those values and be able to pass them into, let's say, other futures. So you might have, say, one future that's computing one value, and you want to take its result and pass it to another future that's required to actually take the value of the first future and then compute something else. All right. The way you would do this in lparallel, because this is kind of the same thing like in shared memory programming, what you would do, well, shared memory multiprocessing, you would end up using a mutex to create a critical section to copy this value into one thing, and then call a condition variable to wake up a thread to actually grab the result and then continue the computation. This is one way of actually doing this if you're doing regular multi-threading. In lparallel, you have something called chain to actually do this. To see this, we can actually just simply run, let's say, lparallel force on, say, a future, okay, of chaining the result of some, say, delayed task that just returns 3. Okay, so what's happening is here is The delay is going to be forced by calling chain on this delay. We're forcing it, and when it's true, it'll go past to the future, and then the future is immediately forced because it goes off to a thread, returns 3, joins, and then we end up getting 3. All right. So this is what it is. So we're able to actually now chain different futures pretty quickly by just simply using this command. All right. Finally, there is um, uh, this is one thing that you could end up leveraging, which is suppose you want to cancel operations. All right, let's say that you had that low priority task that I'm talking about. This is one thing that they used, but I'm wondering if you could use this also in other situations. In the documentation, they had this thing. Let's say you have this low priority task S that essentially called speculate. Oh, not speculation, speculate, and you just compute some value. All right. Um. Oh, sorry. Um. And now let's say that you want to fulfill this guy by changing its thing to being an error, saying that hey, I wanted to actually throw an error saying that the task was canceled. Okay. Um, the way you would do this is you would do first lparallel delay, sorry, lparallel chain on lparallel delay of some error that kind of is telling you the speculation task was canceled. Okay. Now, when you call um, force on S, which is going to force the computation to be completed, what's going to happen is since this is running a thread, right? Futures are running in a separate thread. That error that's popped up into delay, that's getting popped into the chain. Once that chain is fulfilled, it'll end up getting reassigned to some lambda that ends up um, telling our top level uh, future that the task has been canceled. We're not going to actually need you to do any further computations. Um, I thought you could actually end up leveraging regular futures to do this. With you could use a chain. I haven't done any future experiments on this. No pun intended. But it is something that I'm thinking that you could probably leverage this pattern of chain and delay to actually create essentially like workflows where there like think workflows where there might be the need for a cancel button. All right, cancel this operation. Let's say I'm running a long-term I'm writing simulation software, or I'm writing a software that requires you to do a long-running computation, and halfway through some end user requires you to cancel it because they may want to tweak the start of the simulation after seeing some initial or intermediate results. Um, this is where this chain delay pattern becomes important. Whether or not this works with futures or speculative tasks are the only way to do this, I I would encourage that as an exercise for you folks to try out. Um, in the final remaining minutes, like the last 8 minutes, I'm just going to mention um, uh, the fact that um, uh, I found out the other day that it's not just PMAP that ends up that they actually ended up creating parallel versions for, but there's a good number of standard common Lisp functions and or macros that have parallel versions. Plet we saw PMAP and pcount like again, and we also talked about preduce last time. But the logical functions like parallel, they have a p and. Like you actually have lparallel p and that would run multiple predicates in parallel with each other and then reduce their values to something that you could then use. So you could then say p and x is less than, let's say x is greater than 0. Let's do this. To show this, um, lambda x. Okay. Um, let's say that x is greater than 0 and x is less than 5. Okay. And let's say we call that with 3. We see that it's true. We call that with 6. We see that it's nil. But pretty simple stuff. And you all know that this is what the and operator does. The fact that we're doing in different threads makes things a little simpler. If you're trying to do barrier synchronizations and things like this and get results from different threads. This is just a simple example that you could end up leveraging. Additionally, and this is something I've been thinking about as part of our method combination project, pfun_call. Because pfun_call basically says, hey, go into the current kernel and then dispatch this guy. And it just takes in a function, just like just like normal fun call. I'm still trying to determine how to leverage this, but I'm working through it. Uh, so lparallel has one more thing that on top of this that I'd like to bring up, which is some data structures that are separate from the actual data structures that we talked about. Like we've already mentioned about the queue that's available inside of lparallel. I believe it was last week that we actually kind of brought that up. But there's another thing that lparallel had that I thought was process tree, but it's not a process tree. It is a data structure where you um, can wait on the results of other essentially tasks. But in this case, it's you can leverage this for essentially waiting on the results of futures. Um, and in one thing that we could do has before to set this up, we were if you're waiting on the results of futures, you could totally do what I showed earlier, which is using chain and delay. Okay, you could totally go ahead and leverage that to hook up and create your own versions. But it's going to be pretty inefficient. Um, you have also the ability to actually run. Um, you also require it to. You may want it, your futures to run in after they failed. Okay, you may want it to get retried and stuff. So to do all this, you essentially want something like a let star, but a let star that allows you to uh, what's it? Spawn different threads, take their results, and then consolidate them in a single kind of like nice little way of form, so you can look at the dependencies between each of the individual things, right? One way of doing this is, and this is the one that I was actually kind of impressed on. This P tree basically essentially does that. It allows you to essentially create this let star kind of like future design where you have different computations and each computation is dependent upon the previous one. All right. It's usually written in a what's it? The order in which it might be important, but the examples that I've seen, it seems to indicate that the primitive or the triggers part of the computation are lower in the computation tree, um, they're your leaf nodes, and the higher level ones are higher in the computation tree. All right, and the way they represent this tree ordering is by essentially in let, you have the top level computation and then the bottom level computation. So the first element is going to be your root of the tree. What are you ultimately computing? So the example they used is essentially create computing the area of some some geometry, some space, okay, which we all know is width times height. And then we specify, well, what is width? Well, width takes in, let's say, some border, all right, and we're going to go ahead and manipulate some border, all right, and let's say that we take, the border times 2, okay, and then let's say the height is going to take a border 2 as well, and let's say that we do 5 2 times border, okay, oops. And then ultimately we have border, which is a computation, and we just specify 1, okay? And we compute the area, okay? Uh, this here converts itself into essentially a let, okay? But the let essentially is p-tree functions that ultimately are calculated by futures. All right. And notice each of these is essentially got converted into its own lambda associated with the specified name, in this case, area, width, height, and border, respectively. When we run this, this is actually going to be run in um, uh, a way that essentially implements that chain delay function for you. Notice the amount of code that this uh, is compared to how much you would have to write if you end up writing the equivalent, which is something along these lines. I'm going to show you what the generated code would look like. It would be so you may think that you could just leverage something like this, all right, which is just running features and then forcing the borders and then computing each in this order. All right, and you could totally do this. This actually ends up doing exactly, um, oops, oops, 5. I have to put this as a parallel, this as a parallel, parallel. Okay. Oh, I forgot to put it in one more place. 5. There. I lost my thing. Okay. I'll do that. So you could totally do that, but the problem is when you're trying to do parallel computations, and you have a task pool, um, your workers might uh, get hijacked effectively, um, because because each of these are using essentially a blocking call, forces a blocking call. One of them might be sitting nice and comfortably on a thread, waiting for some other computation to complete itself, which may never come. All right. In this example, that is not the case, but there are other cases where you might end up leveraging that. All right. Um, P3s essentially work around this by essentially building and creating those P3 functions that you saw earlier, which essentially is scheduling and setting up the tree of computation. So that way, it can essentially do a depth first look up to see if computations have failed or are locked and they need to be retried. So having that dynamic tree has this ability to now give you the opportunity to essentially uh, what's it essentially take out nodes and be able to restart them. All right, and it avoids essentially the core problem, which is L parallel force on waiting for the value of the future. All right, you don't have to worry about your task pool being suddenly unavailable because you are trying to compute essentially something that someone wrote in this let star fashion. Okay, so P-trees gives you that kind of data structure, and it again goes back to their infrastructure for essentially scheduling these computations. So that's all I have for today. I'm going to open the floor for questions and comments from our audience. And if there aren't any, I will, you know, I will then, close off the talk, and then we'll see you guys in a couple of weeks.
Nope. This is interesting to me. So I don't really have any questions. I'll have to watch it again. But
So if you're doing stuff with data processing, a lot of this stuff, and particularly like scheduling management, it becomes important.
hmm
It's just it's often the case that most people don't they start off with something small um, that's synchronous, and then they try to rewrite a lot of stuff that L parallel gives you just out of the box. So I
okay.
thought I'd complete this discussion. And by the way, I haven't even remotely showed this setup, and this is because I need some time to try this experiment with Docker. But essentially, lfarm would give us the ability to create these dummy like Lisp servers, and it would be pretty neat to try out if I had a set of like containers running somewhere and I knew their IP addresses. I hook them up. Can I do like parallel computations? You know, um,
Yeah.
so so yeah, because that's all high level network programming without having to learn how to write sockets. Which
Yeah.
for some folks is pretty important, and especially if you're writing simulation or either scientific or even high data processing software, having that hidden from you because it's kind of a given is useful because now you're kind of concentrating on what really matters, which is the algorithm.
Yeah.
Yeah.
That makes sense. Okay.
Well, if there aren't any other questions, my audience in YouTube, thanks for joining once again. I appreciate you guys coming. Please like or subscribe to our channel for upcoming videos. Um, I hope if you really like the content, please also post comments for new topics. I do actively look at the comments to make sure that if there are topics that people want me to cover, I make sure I account for them. Um, and if you have any advanced questions on L parallel or Lisp in general, feel free to add your comments too as well, and we'll address them as we can go. And with that, I hope you guys enjoy the rest of your Saturday afternoon. Thanks.